Welcome to the last section of this course, Deep Learning with Convolutional Networks. In this section, we will look at Deep Convolutional Neural Network, DCNN. And then we'll be recognizing CIFAR 10 images with deep learning. Now let's move on to the video, titled Deep Convolutional Neural Network, DCNN. In this video, first we will take a look at shared weights and bias, then pooling layers. After that, LeNet, and finally understanding the power of deep learning. Let's start with Deep Convolutional Neural Network, DCNN. A Deep Convolutional Neural Network, DCNN, consists of many neural network layers. Two different types of layers, convolutional and pooling, are typically alternated. The depth of each filter increases from left to right in the network. The last stage is typically made of one or more fully connected layers. There are three key intuitions behind convolutional networks: local receptive fields, shared weights, pooling. We will see shared weights and bias in detail. Let's suppose that we want to move away from the pixel representation in a row by gaining the ability to detect the same feature independently from the location where it is placed in the input image. A simple intuition is to use the same set of weights and bias for all the neurons in the hidden layers. In this way, each layer will learn a set of position-independent latent features derived from the image. In Keras, if we want to add a convolutional layer with dimensionality of the output 32 and extension of each filter 3 by 3, we will define these lines. Alternatively, we can define these lines. This means that we're applying a 3 by 3 convolutional on a 256 by 256 image with 3 input channels or input filters, resulting in 32 output channels or output filters. An example of convolution is provided in this diagram. Next, we will learn about pooling layers. Let's suppose that we want to summarize the output of a feature map. Again, we can use the spatial contiguity of the output produced from a single feature map and aggregate the values of a submatrix into a single output value that synthetically describes the meaning associated with that physical region. Let's see max pooling. One easy and common choice is max pooling, which simply outputs the maximum activation as observed in the region. In Keras, if we want to define a max pooling layer of size 2 by 2, we will define this line. An example of max pooling is shown here. Next, average pooling. Another choice is average pooling, which simply aggregates a region into the average values of the activations observed in that region. Note that Keras implements a large number of pooling layers. In short, all pooling operations are nothing more than a summary operation on a given region. Let's see an example of DCNN, LeNet. LeNet trained for recognizing MNIST handwritten characters with robustness to simple geometric transformations and to distortion. The key intuition here is to have low layers alternating convolution operations with max pooling operations. The convolution operations are based on carefully chosen local receptive fields with shared weights for multiple feature maps. Then, higher levels are fully connected layers based on a traditional MLP with hidden layers and softmax as the output layer. LeNet code in Keras. To define LeNet code, we use a convolutional 2D module, which is this. In addition, we use a max pooling 2D module. Here, pool size, that is 2, 2, is a tuple of two integers representing the factors by which the image is vertically and horizontally downscaled. So, 2, 2 will halve the image in each dimension, and strides as 2, 2 is the stride used for processing. So now let's review the code. We will create a new file in Atom. You can use any text editor of your choice. First, we will import a number of modules. So these are the necessary packages that we have imported. Additionally, we have imported matplotlib.pyplot as PLT, since we want our output to be displayed in the graph. Next, we will type in np.random.seed and specify the value inside it for reproducibility. Then we define the LeNet network by adding these lines as shown highlighted. So we have a first convolutional stage with ReLU activations, followed by a max pooling. Our net will learn 20 convolutional filters, each one of which has a size of 5 by 5. The output dimension is the same one of the input shape, so it will be 28 by 28. Note that since the convolutional 2D is the first stage of our pipeline, we are also required to define its input shape. Here we have defined it, as you can see on your screen. The max pooling operation implements a sliding window that slides over the layer and takes the maximum of each region with a step of 2 pixels vertically and 2 pixels horizontally. You can see here pool size 2, 2 and stride 2, 2. Now we will define a second convolutional stage with ReLU activations, again by a max pooling as you can see here. In this case, we increase the number of convolutional filters learned to 50 from the previous 20. Increasing the number of filters in deeper layers is a common technique used in deep learning. Then we have a pretty standard flattening defined by this highlighted line and a dense network of 500 neurons, which is then followed by a softmax classifier with 10 classes, defined here in this highlighted part. Then we have specified return model in the softmax classifier. Congratulations, you have just defined the first deep learning network. Let's see how it looks visually. Now we need some additional code for training the network, but this is very similar to what we have already seen earlier. Let's take a look at the code. The highlighted part is the one we added. This time we also show the code for printing the loss, which is defined in the code. Now, as we made necessary modifications that we need, we will go ahead and save the file. So save as Keras LeNet.py. So the file is successfully saved. Now we can go ahead and run it. It's time to run the code. So type Python followed by the name of the file. You can ignore the warnings. Here it says it uses TensorFlow as backend, and then it will train on 48,000 samples and validate on 12,000 samples. This may take a few hours of yours. As you can see, the time had a significant increase, and each iteration in our deep network took more than 500 seconds against 1 to 2 seconds for the network defined in the first section. However, as you can see that the accuracy has reached a new peak at 99.13%. So we got the model accuracy graph as seen on the screen, and we also got the model loss graph, which you can see now. Next, we have opened up the Keras LeNet.py file to change the epoch value. So inside the network and training block of code, we have NB epoch value as 20. We will change it to 4 and save the file. Then we will open the terminal and run the same Python file again, which help us to plot model accuracy and model loss. We can ignore the warnings. The model will train only for 4 iterations as we have changed the epoch value from 20 to 4. This may take a bit of time. We have got the model accuracy and model graph. So with these we understand that we can train in only 4 to 5 iterations to achieve a similar accuracy, which is close to 99%. So here we achieved the test accuracy of 98.74% in just 4 iterations. The highlighted line also shows the final accuracy achieved by our model that we have trained. Let's see some of MNIST images just to understand how good the number 99% is. For instance, there are many ways in which humans write a 9. One of them appearing in this diagram. The same holds for 3, 7, 4 and 5. The number 1 in this diagram is so difficult to recognize that probably even a human will have issues with it. We can summarize all the progress made so far with our different models in this graph. Our simple net started with an accuracy of 92.22%, which means that about 8 handwritten characters out of 100 are not correctly recognized. Then we gained 7% with the deep learning architecture by reaching an accuracy of 99.2%, which means that about 1 handwritten character out of 100 is incorrectly recognized. Lastly, we will be understanding the power of deep learning. As we can see in this graph, our deep network always outperforms the simple network, and the graph is more and more evident when the number of examples provided for training is progressively reduced. With 5,900 training examples, the deep learning net had an accuracy of 96.68%, against an accuracy of 85.56% of the simple net. More important, with only 300 training examples, our deep learning net still had an accuracy of 72.44%, while the simple network shows a significant decay at 48.26%. All the experiments are run for only 4 training iterations. This confirms the breakthrough progress achieved with deep learning. At first glance, this could be surprising from a mathematical point of view, because the deep network has many more unknowns, the weights, so one would think we would need many more data points. So here we have come to the end of this video.